Welcome to today's webinar. The topic today is 9 special features in Rfem 6 you should know. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will also be the presenter. My colleague Mark Gebhardt will support me by answering your questions during the webinar. He's responsible for customer support and he's a member of the product development team, geotechnical analysis. Okay, I show you how you can ask questions, at least for the attendees who participate the first time. First, I switch off my webcam that you can see the full screen. Now just press the button with the question mark, then enter your question here in that field, press send, and Mark will receive your question and he will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, to the agenda today. Those are the 9 features that I would like to introduce you. Very valuable features, but you will use some of them not so often, other features more often. In my opinion, for example, you won't use the intersection so often, but the surface result adjustments is such a feature that you will use more often. And those are the other features I prepared for every feature a model, and I will explain the function of these features in the program. Let's start in Rfem with the first model and the first feature. You can find all features under Insert, Special Objects, where are not only 9 features, because there are 2 new features, the design strips. That's a feature what is often used in the American market, and we also prepared a webinar about it. Maybe my colleague can share the link in the chat to that webinar about the design strips. Okay, let's start with the intersection. The best way is to select all the surfaces and then create the intersection. But as you can see, that's not a surface, it's a member at the moment. With a right click, I can go to member and then generate surfaces from member. And now where are all objects surfaces. And we would like to create an intersection, and at the end, this part of the tube should remain and not this one. And we would like to have a hole in that surface. Okay, so let's select all, then with a right click and move to surfaces. We can create the intersection. Maybe, at first to the definition of the intersection. If surfaces intersect and internal forces are transferred on the contact points, it's necessary to create an intersection. This prevents the creation of independent and unconnected subsystems. And this function create intersection, only the intersection line is created. I can show that. You can see only this line is created. I undo all, then I open the dialog again. Then divide by intersection. The intersection will be created and subsurfaces will be created. And with this function, additionally, the intersection surface is deleted. So we will use that function. And you can see there's also a hole. So, and we can easily delete this part of the tube. But if you have got more complex models, then I recommend to go in the navigator data. Then you see all the surfaces, and then you can select the single surfaces to show what or to see what you will or need to delete. For example, with a right click, I can delete with boundary lines. Okay, so I can also delete this line that was the middle line of the member. And now we have a correct model. Okay, that should be all to that feature. We turn to the next model and the next feature. So I would like to explain the surface result adjustment. You will also find it here, insert special objects. So, but at first I would like to say some words about the surface results adjustment. That it describes an area in the model whose graphical results are not represented by the actual diagrams, but as mean values. You can use a user-defined adjustment area to evaluate the smoothed surface internal forces. And in Rfem 5, this was called average region, and now the name is surface result adjustments. We have that surface here. That's the CLT slab over a wall. And you can see there are quite high internal forces only on that point. And we would like to smooth that internal forces. To compare the results, I would like to copy that model. So create a copy, 6 meters, and copy including loading. Okay. So, and I create the surface result adjustment only on that point, and we will compare it with the other point. Okay, then in the menu, insert, special objects, surface result adjustments. Okay. Here we have different options for the shape, rectangle, circle, ellipse, and so on. The dimensions should be 20 centimeters by 20 centimeters. Then I select the endpoint of the wall and move it 10 centimeters in minus y direction. Okay, and I also have to select the surface. That surface. Okay. So then we can calculate all. Okay, and you see that's the highest value, but that's the value what we have in the original model, 19.5. So, and let's check what the value is, or the highest value for that surface. I deselect the original model. Yeah, and you can see now is the or highest minus value, the lowest value 16.0. Let's turn back to the surface result adjustments. I go back to special objects. You can see it here. Maybe some explanations or additional explanations of the different adjustment types. This averaging of these values, that's the default setting for basic internal forces in surface direction y, and this is the average or the default setting for basic internal forces in surface direction x. So then contact stress area. This option is currently only relevant for the steel joints add-on. Then user defined. The results of selected types of internal forces are averaged. In that case, mx, but you can select more if you want. That's not a problem. As you want. Then 0. These results within the area are set to 0. You can also select the single basic internal forces. Okay, and none. The surface internal forces are not averaged, but displayed in a regular way. When you want to average only one direction. Okay, so that was an additional explanation. Okay, that should be all for that model. Turn to the next model. And the next feature that I want to explain is the surface contact. A surface contact describes the connection between parallel surfaces. It is a coupling of surfaces by which you can control the transfer of forces without creating a contact solid, as was the case in Rfem 5. And this allows you to connect surfaces whose contact is, for example, only effective for compressive forces. And that's what we would like to model here. That's a member created by surfaces, and that's a concrete surface. Let's display it in the navigator display with the real thickness. So surface filled including thickness. That looks good. But in reality, in our model, it's not connected yet. So, and we would like to create the surface contact. This time in the navigator data, that's another option, special objects. Then right click on surface contacts, new surface contact. At first, this surface, okay. And then the flanges, the two flanges of the member here. Okay. Okay. So let's calculate all. The contact is there, but you can see it's rigid connected on all sides, on both sides of the concrete slab. But we would like to define it that it can lift it up on this side, yeah, that the member lies loosely of the concrete block. To compare it better, I copy all in y direction, 2 meters, 2 meters, create a copy and including loading, okay. So, and I modify this surface contact. Not a full force transmission, but a new surface contact type. Failure under tension, yeah, that can be lifted up. And in that case, rigid friction, I define only a very small friction coefficient. But that's very important here. Okay. Then we calculate all. Yeah, and now you can see the difference. It can, yeah, lift up here on this side. I can also show that on the contact stresses. Now you can see in the original model there is compression here and tension on this side, and on this model there's only compression on the right side and no tension on this side. Okay, that's all to that feature. We turn to the next model and the next feature. Rigid links is the next feature. By using rigid links, you can model connections between lines, members, and surfaces without defining coupling members or rigid surfaces between the objects. Deformations of coupled nodes, lines, and members are identical for a rigid link. In that model, I could also define surface here, rigid surface. But yeah, with that feature, it's quite easier. The real advantage of this feature is the objects can be placed on their actual location. When I turn to the navigator display and select filled including thickness, you can see all is on that place where it really are. So, and now I create the rigid links. So insert, special objects, rigid links. In our case, line to surface. That's the line, and that's the surface. And you can see the line in the surface is automatically created. Okay. So now we can calculate all. Okay, that looks quite good. I would like to show that on a more practical example, I think. That's a timber concrete composite beam. You can see that's a concrete surface on their actual position, and that's the timber member. And we can also go to the navigator display and select filled including thickness. But we need to create the connection. So special objects, rigid links, right click, new rigid link, line to surface again, the middle line of the timber member and the surface. Okay, and this line is created automatically. And we have to deselect that option, ignore relative position, because we would like to consider that the member is below the surface. Okay, so let's calculate all. At the moment, we have a rigid connection between the surface and the member. And that's not really correct, because there are joints for this connection, and we are not rigid. And that's why we need to select a line hinge. So how to do that? We take a look at the result. I think you can't really see it. Okay. 6.8 is the deformation in that point. Then we do a double click on the rigid link, and we create a line hinge now for the connection of the two parts of the member and the surface. And we create a spring, or define a spring constant for the longitudinal direction of the member. So 370,000. Okay, it can be nails or something like this. Okay. We had 6.8 for the deformation, and now it should increase. Now where are 7.6? It was increased. Okay, then we turn to the next model and the next feature. The next feature is the structure modification. I would like to display it on that model. I use the model that you can find in the Dlubal Center. Just a moment. I have to move it to the right screen. So, okay. You can find it under examples, projects, examples, and that's the model. Okay, and I turn to the base data. I selected the add-on structure stability, and I did a stability analysis. But at first, some words to the definition of the structure modification. It allows you to individually adjust stiffness of materials, objects, and object types. Furthermore, selected objects or nonlinear objects properties can be deactivated for the calculation. Structure modification must be assigned to load cases or load combinations. We will do that later. I show you the design situation where I selected the structure stability. So I turn to the combination wizard, and I selected the stability analysis. So, and under static analysis and design situation number 1, I can find the minimum critical load factor. That's 3.6 and the combination number 13. So let's turn to the stability analysis and the combination number 13. And you can see the critical load factors or the mode shapes are that those are not global mode shapes, but local. For this member and this member and so on. And I would like to see a global mode shape. Yeah, I could select or calculate more critical load factors, maybe 40, and search for the first global mode shape, or I use that trick. So I turn back to the design situation, number 1, then to the combination wizard. So, and I consider structure modification, and I create a new structure modification. That's what I said at the beginning. You can modify the stiffness of material, section, members, and so on, member hinges. Let's do that as an example for the sections. So, and I increase the moment of inertia factor of the coupling members and these members in the first row. So factor of of 10 here. For IY and IZ. Okay. 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 Yes. Okay, those are the members. This member and this coupling members. So then let's calculate that, or we can do the static analysis. That's okay. That should take some time. We have 100 combinations. Then at first the static analysis will be done, and then the stability analysis, ST. But you can see I have more than one course, and it's a parallel calculation. But we need to wait some seconds. Yeah, and the result will be, because we increase the stiffness of the coupling members and so on, that we will get a global mode shape for the first mode shapes. So let's take a look at the stability analysis. Combination number 13. Okay, and you can see the first mode shape is a global mode shape. Also the second and the third and so on. Okay. Yeah, just use that function only for such things, and not you don't or you must not increase the stiffness of single members only for such calculations here. It's as a trick. Okay, then we turn to the next model. And I would like to explain the nodal release. With a nodal release, the model can be decoupled at a specific location. You can use it to model, for example, a beam lying loosely on the top of each other. I created this simple model, and I would like to model that this one, this member lies loosely on the top of this. So insert, special objects, nodal releases. Then node number 5, okay. Then I will release, or would like to release, these two members. Okay. So then nodal release type. I create a new. So, and for the set direction, non-linearity fixed if positive reset. Okay. Then I have to define a local access system of this member. Okay, that should be all. Okay. Okay. So then I create a load in minus z direction, minus 30. Okay. So, and now it should lift it up. Okay, that works. We can change the direction. Okay, and now the deformation in the middle point should be the same. Okay, good. That was all to that feature. We turn to the next feature and the next model. Line release. I prepared that model, but what is a line release for? A line release allows the model to be decoupled along a line. You can use it to model, for example, two surfaces being loosely connected or transferring only compressive forces at the common boundary line. For this model, you can see where is a moment over the support. Yeah? But we would like to connect this surface with this surface hinged. So, and for that is at the moment a composite beam. It's rigid connected, the surface and the member. You can see that on the moment at the end, and that's why we would like that, or to define that the member is longitudinally movable. Okay. So we start, insert, special objects, line releases. Okay. That the line is this one. Or just a moment, to compare the results better, I would like to copy the surface again. Or all components. Copy 6 meters or 7 meters. Create a copy with loading, okay. And we will define only the line releases only for this model. So again, insert special objects, line releases. So line number 11, okay. Then the surface number, this one, okay. Then I have to define a line release type, and I would like to create a hinged connection. Okay. So, and another line release on that line. Insert special objects, line releases. So line number 9. Okay. Member number 2. Okay. And I create a new line release type. And I create a very small string that it also calculate the model. That's not completely movable. A very small string constant. So let's calculate all. Okay, now you can see the connection is hinged between the two surfaces, and there are also no moments at the ends of the member because it's longitudinal movable, and that connection. Okay, that was all for that feature. Then I would like to explain the feature surface release with this model, maybe a definition of the surface release. With a surface release, the model can be decoupled on the surface. You can use it to model, for example, solids being connected in an unbraced manner or transferring only compressive forces on the contact surface. I would like to explain that on that model. That's a bolt, and you can see in that plate here are tension basic stresses also on this side, and that's not correct. The bolt is at the moment glued on all sides here of the hole, and the real behavior should be that it's compression on that side and no tension on this side. Okay, and with this surface release, it's not necessary to create a contact solids between the two surfaces. So to see the difference better, I create a copy, 10 centimeters in X direction and including loading. And we will compare the results better when we see the two models. So then I select only the bolt. I can do that with this function, but when you have got a larger model and you would like to select only the bolt, when I press nothing, I can't select it. And the trick is to press the Alt key. So, and then you can select only that bolt. So then only this should be displayed. And now I create the surface release. So this time with the navigator data, special objects, surface releases, right click, new surface release. So surface number, this one. Okay. So then surface release type. So I select a nonlinearity here, fixed if positive p set. That only compression is transferred and no tension. Okay. So, and we would like to release the solid number. We have to display all now. Number 6. Okay. That's all. So let's calculate all. So now you can see the difference better. Let's deselect the bolts, then we will see it better. So hide selected objects. Okay. Now you can see the tension here on that side, and the tension is near to 0 on that side, and we have only compression on the right side. Okay, I hope it's clear now. I deselected not this side of the board. Yeah, but yeah, it's the same result. Okay, that's all to that model, and we turn to the last feature for today, the blocks. You can reach the blocks with the block manager, and that's a huge database of beams, trusses, frames, bracings, and so on. And as an example, I would like to show it on a storage, on a silo. Okay, I select this one. And you can define for the blocks the parameters. I will show that as an example here. For example, in that case, the shell height, shell radius, and so on. Let's change some parameters. The shell height, then maybe the thickness should be a little bit higher. Maybe 8 millimeters. Okay. Then you can also create hydrostatic pressure for that model. Let's change some parameters, 500. That's okay. I have to modify or create a new load case. Filling and action category imposed load. Okay. So, and now let's create the model. I created that's in the same model here. That was a mistake. Let me turn to the prepared for the empty model. I do it again, just a moment. So the silo change the parameters again. Eight millimeters. So. So filling. Okay, and I changed the German spelling to English. Self-weight. Okay. So you can see also that load case is created and the model, and you can change the parameters of the block anytime. Sorry, that line I have to click. I can edit the block also later. Okay. So that should be also all for this feature. That's also the end of the webinar. I hope I could explain you features that are valuable for you. You can decide it by yourself. Just try it. You can download the models from the page where you can also find the recording and the PowerPoint slides. In the next days, you will get a link via email to the page. Okay, that should be all for today. I thank you for your attention. Thank you, Mark, for answering the questions. I hope we meet each other in a future webinar. Have a nice rest of the day. Bye-bye.